This last topic about integration. So this is notes on integration. Notes. This is chapter 4, I believe. Yes, chapter 4 in the book, 4.1. Integration. Gradation. And I'm going to call this and area under the curve. Area under a curve. Because that is what an integral is. An integral is an area under a curve. So we're going to start talking about integration visually. We're going to get the idea of it, and then we'll talk about, again, like the mathematics behind it. Similar to how we did derivatives, right? Similar to what we did with derivatives. What is a derivative? We're going to talk about what is an integral. What does it do for us? How does it work visually in a graph? So an integral is the opposite of a derivative, right? Area under a curve. So let's say, for example, let's say that you have a car. A car drives 30 miles per hour for 2 hours. Car drives 30 miles an hour for 2 hours. This is an example of a situation, right? Like a description of some real life scenario. My question is, how far did the car go? What is the distance that the car traveled? What is the distance that the car traveled? It was driving 30 miles an hour for 2 hours. How far did the car go? Who wants to answer? How far? 60 miles. Seems reasonable. How'd you get that, Pariso? Pariso, where'd that number come from? How do we do this problem? How do we think about this logically? In our mathematical minds, how do we analyze this situation? Well, we know we have a speed, right? Here's a speed. This is in miles per hour, right? And here we have a time. Time in hours, right? And we know there's a formula, right? The distance, 30 miles for 2 hours, right? 30 miles and 30 miles, right? 2 times, right? 30 times 2 is 60. Very good. So we know that like distance equals a rate times the time. This is like logical. You are going this speed for a certain amount of time, and you multiply. You'd say, okay, 30 miles per hour, 30 miles per hour times 2 hours. What ends up happening, if we analyze this, we can see that the hours cancel out. We're looking at units, right? We can think of this like the units cancel out. You've done this in chemistry, sort of unit analysis. And this basic idea will give us just the miles. That's going to be 60 miles. So we multiply these two, right, and get our answer, and the units cancel out. We have this kind of analytical situation. We can think about distance and time and multiplying them to cancel these units. Cancel these units. Let the units cancel. Units cancel. And we get 60 miles. That's why we get a distance when you multiply a rate times a time. This is why, because the units cancel. Mathematically, theoretically, this is why this happens. And this is why units are very important in math, and in particular AP Calculus, because you need to analyze, well, what is the unit, what's the situation, how can I get the information I want from the units that I have. And this is why when you multiply these units, they cancel out, and we're left with miles. So that's how it works, right? This multiplication. If we were to look at this situation, not just like visually, not just algebraically and with these words, but if we were to look at this visually, this is what it looks like on a graph. Visually on a graph. We could look at this situation graphically. We can say, okay, here's a graph. I've got my speed on this side. I've got my time down here. Time in hours. I've got my speed in miles per hour. We can look at this as a graph. We can say, okay, here is 10, 20, 30, right? Here's 30. And here's 1 hour, 2 hours, 3 hours, 4 hours. We can look at this as a graph. And we can see that, well, okay, if I were to take this graph and I said, okay, I'm driving 30 miles an hour for 2 hours, my graph is going to be a straight line. Should I do this in, I guess this is fine. 30 miles an hour, straight line, across here for 2 hours. Maybe I'll just continue it for the rest of the time, right? 30 miles an hour, driving 30 miles an hour for 2 hours, right? Let me stop doing that. Let me do here. For this 2 hours, right here. 2 hours, right here. Come on, straight line. Oh, goodness gracious. Here we go. 30 miles an hour for those 2 hours. So what we just did when we multiplied the rate times the time, my rate is here. Here's my rate. This distance here is 30 miles per hour, right? And this space here is 2 hours. Give myself a little more room here. Hold on. This is 30. This is like this distance, the height. I could think of this as a height is 30 miles per hour. And this distance across on the bottom is 2. So if I were to multiply, what I'm really doing, visually what I'm doing, is I am creating a area here. I'm finding the area of this space in the graph. Area equals I'm doing the 30 miles per hour times the 2 hours. We are finding the area under this curve, under this graph, visually to create this distance equals the distance, the area equals the distance of 60 miles. So this area here is 60 miles. This area under the curve, below this graph, up to 2 hours later, this is our distance. And so we have this visual representation of the same idea where you're finding the formula, but we're doing it visually with this curve. And this is what an integral is. This area is an integral. The area is called an integral. When you integrate a function, you are looking for the area of that function under some curve. You can think of it like you are accumulating, you're adding up a bunch of pieces of this of this graph? Yes, you have, Perry, so this is exactly correct. You have been doing this your entire lives. When you find distance, you have been doing it exactly like this without really seeing it in the same way. So you've been doing integration of some simple kind of problems, right? Speed, rate times time, some kind of rate multiplied by some kind of time will give you this answer of your integral, right? And we can do this with all kinds of different rates, right? You can do like, if you're getting, for example, another example you can do, if you have a tank filling with water, right? The flow is, let's say, I don't know, 5 gallons per minute. And the time, if you do the time, let's say it's 20 minutes. How much water? How much water is in the tank after those 20 minutes? Well, you do the same thing, right? We take 5 gallons per minute times 20 minutes. Right? The minutes are going to cancel out, and we end up with 100 gallons. Same kind of idea with units, right? You're multiplying these units, canceling out, arranging what you want. And the reason that works is because of exactly what we did up here. The reason that works is because we have this graph, visual representation, where we find area under a curve. And that area is what we call an integral. That area is what we call an integral. So this is a simple example of what you can do with this idea of areas. You can find an amount. You're finding an amount given a rate and given a time. Usually it's a rate and a time. Some amount of speed or flow rate, or let's say people walking into a building, 10 people per minute, and how many minutes, and you can do all this kind of calculation where you're finding out these rates, and you can use that information to multiply together to create an area under this curve. Now, the part that's calculus is that these graphs are not straight. The part that's calculus is we have more complex graphs. Graphs, or functions, I should say functions. Functions are not always lines. For example, let's say my speed of my car, my speed here, I start at rest, this is time, speed of a car. Your speed increases, reaches some maximum for a while, and then comes back down, and you stop at the next place, right? Your speed is not linear. You have this kind of curvy area. Sometimes we have this speed goes up and then it comes back down. Maybe it even goes up and then back down and then up and then faster. Like maybe it could look like some crazy thing like that, right? We have complex curves that we need to find, and with this, how can we find the area? How can we find the area under this curve? And this is the part that leads us to calculus. We have this challenging shape. It's not a straight line. I can't just use like geometry, right? It's not like a triangle, or it's not like a circle. It's not some solid shape. It's this wiggly shape. How do I know what the area is under this curve? Well, what we do is we split into rectangles. We split this curve. We imagine, okay, let's cut this time into like chunks. Let's cut it into pieces like this. And from each piece, let's imagine a rectangle for the area under that curve, right? We're going, oopsies, we're going up to where the curve is, and we imagine doing a little rectangle filling in the area, right? We go up to here, and we use these rectangles to approximate the area under the curve. We use these rectangles, and we split it into these chunks, and we use these pieces, and we find the area of each of these rectangles. And using these rectangles, we can get an approximation of the area under the curve, right? Using these rectangles, we can approximate the area under this curve. And sometimes the rectangles are too big. There's like extra. And sometimes the rectangles are too small. Missing pieces, missing. But overall, we can kind of get a pretty good approximation and use the rectangles to approximate the area under the curve. Sometimes you have extra stuff. Sometimes you have some missing areas, right? Like extra bits that, like, the rectangle's too big. Sometimes the rectangles are too small. But overall, we can get a kind of, at least get close to the area of under this curve, right? This distance here between the rectangles, we call this distance delta x. The kind of width of the rectangle. Width of the rectangle. And that delta x can change. You know, you can have some rectangles that are wider, some are smaller, but we'll get to that later. But each of these distances of the rectangles, this width of the rectangle, we call that delta x. The height of the rectangle, how do I do this? The height of the rectangle here, call this the height of the rectangle. That is f of some value here. F of let's call it, well, let's call it C. It's the function value. It's the height of the function here. F of C. It's the height of the function. So we have this function value, this function height here, times the width of the rectangle, and we add together all the different rectangles to get the approximation of the area under this curve. So add together all of the rectangles. You're going to do f of c times delta x for each one, right? C1, you call this C1, C2, C3, C4, C5, all these different ones, right? All these different C values. You have all these different numbers, right? All these different spaces where the different heights. Here's one height for the rectangle going up to this spot. Here's this height. Here's this height, right? I guess I can call this C sub I, right? Call it here. Hold on, everybody. Call this C sub I. C sub I. It's that particular number. Use a subscript I. We say this particular number, C sub I, f of that particular value right here. This is like one of the x's. Here's another x. This is another one. This is another one. This is another one. Each of these different heights, they're all different heights. Multiply those different heights times this delta x value, and you add up all the rectangles together, and that gives us the area. When we say sum them up, we say add together, that means we do this. We do the summation. We add together all the little heights, height times width, and we add those all up together using the sigma. Remember our sigma, our friend sigma here, summation. Michael Jones, you weren't in our pre-calc class. This is our sigma notation. This means add them up, right? Add them up together. All these different heights times all these different widths. All those rectangles get added up and they equal the area under the curve of our graph. And this is where we get to the calculus part, adding up all these rectangles. Now this is pretty good, right? I got a lot of rectangles here. It's pretty good. But can we do better? Right? Calculus, we want to know the exact. I want to know the exact area under this curve. Some of these rectangles are too big, some are too small. Right? Some are too big, some are too small. How do I get the exact area? Well, the way that calculus does this, to find the exact area, we add more rectangles. We add more rectangles. So we make the little space, right? We make the width of this smaller and smaller and smaller. We shrink the width down until when, do you think, everyone? Until when? Until that width becomes 0. We make more and more rectangles. We make the rectangles smaller and smaller until the width of those rectangles becomes 0. And once it's 0, we have an infinite number of rectangles. We have exactly the area under the curve. Add more rectangles until delta x reaches 0. And what we call this in calculus is we call this a limit. So here's what it is, right? Here's what we have. When you do the sum of f of ci times delta x, and we do the limit as delta x goes to 0, this is called the integral of f of x dx. This is the integral. Is the exact area, right? And the limit as x approaches 0, this is, so we have an infinite number of rectangles, right? The width goes to 0, making infinitely many rectangles. And this is what we call the integral. This integral symbol, by the way, comes from the sigma notation. This symbol here, it's just another version of adding together. In this case, we're adding together an infinite number of things. That's why we do the curve here. It's an infinite curve, right? So as the delta x goes to 0, when you have an infinite number of rectangles, you get the exact area, which we call the integral. And so this is the definition of integration, finding these areas, finding this amount, right? Some amount of a value. Let me show you a few things. Let's see. Questions about this? Let me show you some, let's see, where's a good one? I had this. No. I had some little pictures I wanted to show you. Where'd they go? Oh, here we go. So, oh, it's not working. I guess let's do it this way. So the idea here is that the rectangles get smaller and smaller. As the rectangles get smaller, we get a better and better approximation of these curves. Hold on. Let's see if I can do this here. Okay, great. That one, that one, and that one. So for example, let me show you here. So here's an example of what it looks like when you increase when you decrease the width of the box, you increase the number of rectangles, right? So there's really bad approximation, gets better and better and better and better and better as you get closer and closer. Right? The more rectangles you add, the closer you get to the actual area under the curve. Right? Same thing here. Adding more and more rectangles until you get closer and closer and closer to be exactly under the curve. And when you get to an infinitely small rectangle, that means you have exactly area under the curve. Or like this equation here, right? It gets closer and closer and closer to the actual area. So this is what we're doing when we're doing an integral. As the limits of the space goes to 0, as the distance between the delta x goes to 0, you get a perfect curve, perfectly situated under the curve. So just like when I said for derivatives, when I say derivative, you say slope of the tangent line, right? That's the derivative. The definition of a derivative is a slope of the tangent line. It's the rate of change. A derivative is a rate of change. We had these multiple meanings for what derivative meant. A derivative was the slope of the tangent. A derivative was the rate of change of the curve. Was the curve going up or was it falling down, right? Is it a growing, is it positive, or is it negative? It's the rate of change of something, right? If I have a certain, like if I go a certain distance in a certain amount of time, my rate of change, my change in distance over change in time, that's a derivative. We have similar meanings, multiple meanings, for an integral. where'd it go? The integral is the area under a curve. That's the definition of an integral, right? Integral is the area under the curve. It's also the limit of this summation function. The limit of this summation function is an integral, right? It's an amount, right? An accumulation, the exact area, or an amount accumulated over time. Accumulated over time. We have these multiple meanings of integration. It's an area under a curve, the exact area under the curve. Right? It's the distance that you've gone, the amount of distance that you've gone over a certain amount of time, as well as a few other meanings of this we'll go over next time. I just want to show you this one. This is the fundamental definition of an integral is the area under this curve, and we use that area, right, multiplying the rate times time to get some amount. An integral is an amount of stuff you've gained, what you have, what you've added to. So I want to show you how to do some of these problems now. Oh, actually, I have a thing before we get to that. We're going to do some problems. But let's take a look at integrals now. Let's think about these and think about the rates and the accumulation, what it means to accumulate things, what it means to have an area of something under a curve. Let's take a look at that.